At this exact moment in the spring of 2026, humanity is routinely creating localized temperatures of over 100 million degrees Celsius.
Yeah, right here on Earth.
Right here, I need you to pause and let that physical reality settle into your mind. You are sitting there, breathing the air of a planet where the raw, terrifying fire of the stars has not just been captured in a laboratory, but is actively being wired into our electrical grids.
It's a profound and frankly unnerving realization.
It really is. The cosmic code that powers the universe, the very mechanism that illuminates the night sky, is literally in our hands, and we're trying to plug it into a wall socket.
We've completely left the era of basic physics experiments. I mean, what we're witnessing right now is the sheer brute force scaling of an entirely new reality.
Yeah.
To put the scale of this paradigm shift into perspective, by early 2026, over $13 billion in private capital has been poured into this specific pursuit.
13 billion, that's insane.
It is an astonishing mobilization of resources, and it's completely bypassing traditional timelines. We are building machines, tokamaks, stellarators, magneto-inertial systems.
Just massive machines.
Right, to artificially replicate the mechanics of the cosmos. And the stated goal is to save our planet's climate, obviously. But the underlying reality is that, in doing so, we're fundamentally altering our relationship with energy, with matter, and ultimately with the universe itself.
It feels like a threshold we are crossing, one we just cannot step back from. I mean, we're going to explore how humanity is transitioning from digging up dead plants to harvesting the mechanics of the cosmos. So let's look at the actual architecture of this shift.
Structural pathways, right?
Yeah, starting with the tokamak. It is symmetrical. It is relentless. And we've just seen France's West machine hold a high-temperature plasma for over 20 minutes.
Which is an eternity in plasma physics.
An absolute eternity. And China's East held stable plasma at extreme densities for nearly 18 minutes. And then, in April 2026, the United States shipped a 135-ton central solenoid to the ITER project in France.
It's a massive piece of hardware.
Just picture that. A 135-ton superconducting heart designed to beat inside a synthetic star.
And that is the traditional massive scale approach. To really understand why it looks the way it does, we have to look at the geometry of it all.
Okay, lay it out for us.
So the tokamak is essentially a hollow, symmetrical donut or a torus. You inject a gas, typically isotopes of hydrogen, and you heat it until the electrons are stripped from the nuclei.
Turning it into a plasma.
Exactly. Then you use immense magnetic fields to squeeze that plasma so tightly that the atomic nuclei actually overcome their natural electrostatic repulsion and fuse together.
Which is incredibly hard to do because they naturally want to push away from each other.
Right, they repel. But creating that magnetic cage is the ultimate engineering challenge. The tokamak relies on a combination of external magnetic coils surrounding the donut and, crucially, a massive internal electrical current running continuously through the plasma itself.
Wait, so the plasma isn't just sitting in the cage, the plasma is actively part of the cage.
Precisely. It's a closed loop. The external coils create a magnetic field that runs the long way around the donut, which is the toroidal field.
Right.
But to keep the plasma from drifting outward and hitting the walls, you need a second magnetic field wrapping the short way around, the poloidal field.
And how do they make that one?
In a tokamak, this secondary twisting field is generated by driving millions of amperes of electrical current directly through the superheated plasma. The plasma literally acts as a wire.
Oh, wow.
But, this design has an inherent fatal vulnerability. Because it relies on that internal current, tokamaks are highly prone to violent plasma disruptions.
Because if that internal current falters for even a fraction of a second,
the magnetic cage unravels instantly. The plasma instantly loses confinement, crashing into the reactor walls with devastating thermal force.
the walls just get vaporized.
Well, they're struck by temperatures exceeding those at the center of the sun. It is a symmetrical brute force approach, and maintaining that delicate balance of extreme heat and immense internal current is incredibly difficult to sustain.
Yet, despite that knife-edge vulnerability, we have Commonwealth Fusion Systems, CFS, building their spark machine right now, aiming to hit a net energy gain by late 2026.
They are moving incredibly fast.
And the thing that makes this so immediate, so visceral, is that in April 2026, they officially applied to connect their upcoming ARC commercial plant to the PJM grid in Virginia.
Yeah, that was a huge milestone.
I mean, we aren't talking about a sci-fi future anymore. We are talking about connecting a miniature sun to the power grid of Chesterfield County.
That's the astonishing acceleration of the tokamak pathway. They believe they can control the disruptions through advanced sensors and brute force magnetic strength.
But there's another way.
Right. Yeah. While CFS is pushing the tokamak to its absolute limits, there is a completely different architectural philosophy running in parallel, one that attempts to solve the disruption problem by eliminating the internal current entirely.
The stellarator.
The stellarator. If the tokamak is a symmetrical brute force machine, the stellarator is one of twisted elegance. It's fundamentally asymmetric.
I look at the designs for these stellarators, and there is a genuine sense of awe, but also, I don't know, a deep unease. They look like something organic, almost alien.
They look that way because of the physics they're trying to achieve. A stellarator is designed for continuous, steady-state operation. It does not rely on a current running through the plasma.
So no plasma wire.
Right. The entire magnetic cage, both the long way around and the twisting short way around, is generated entirely by external coils. Because there's no internal current to falter, a stellarator is fundamentally disruption-free. It simply hums along steadily.
But if it's so vastly superior and doesn't violently explode when the current drops, why haven't we been building stellarators this whole time?
Because the mathematics required to design those external coils are agonizingly complex.
How complex are we talking?
To generate the perfect twisting magnetic field without using the plasma itself, the external magnets cannot be flat rings. They must be non-planar. They twist, fold, and warp in three-dimensional space in a geometry so chaotic and mathematically dense that for decades, human minds and human hands simply couldn't calculate or manufacture them.
We just didn't have the processing power.
Exactly. We knew the theoretical shape of the cage, but we couldn't build it.
And this is where it gets incredibly surreal. We couldn't build the invisible magnetic cages, so what changed? We handed the problem over to artificial intelligence.
We did.
We are now using silicon brains to rapidly sculpt these invisible, non-planar magnetic cages, optimizing the chaotic geometry in seconds so they can hold a piece of the sun. There is something intensely unsettling about an AI dreaming up a cage of pure magnetic force that a human couldn't even conceptualize.
It's the ultimate convergence of two epoch-defining technologies, machine learning and thermonuclear physics. The breakthrough happened with Germany's Wendelstein 7X facility, which proved the viability of this design shift. Using supercomputers to map the coils, they maintained a stable, disruption-free plasma for 8 minutes.
8 minutes of just perfectly contained fire.
Getting an energy turnover of 1.8 gigajoules, the plasma just sat there, perfectly contained in a cage of twisted math. And now, private companies are aggressively scaling this AI-optimized approach. You have Proxima Fusion developing the Alpha Stellarator.
They just got that massive backing, right?
Yeah, a massive conditional pledge from the Bavarian government for a €2 billion test facility. And Japan's helical fusion is pushing forward with their Helix Haruka design.
But even with AI designing the blueprints, the physical reality of building these things is a monumental burden. I mean, Type 1 Energy is planning a 400-megawatt stellarator for the mid-2030s. We were talking about constructing a massive, continuously burning star core held together by magnets shaped by algorithms.
It's a logistical nightmare.
Every single twist and fold of the metal has to be perfectly aligned to the millimeter. If one massive coil is a fraction of a degree off, the invisible cage leaks and the star bleeds out.
Right.
There's a strange comfort in knowing it won't violently disrupt like a tokamak, but the sheer complexity of assembling these twisted coils is staggering.
In that structural burden, the sheer nightmare of manufacturing massive, intricately warped superconducting magnets is precisely why some developers are abandoning the massive static magnetic cages entirely.
They're just walking away from it.
They're stepping back, looking at the engineering required to hold a steady, continuous star, and deciding it is simply too complex. Instead, they're looking at pulsating dynamic systems.
Which brings us to the alternative, pulse confinement, specifically the field-reversed configuration, or FRC.
Yes.
This is the pathway being championed by Helion Energy. And this is where the physics shift from being incredibly complex to just completely mind-bending. Helion isn't trying to hold a steady sun in a twisting donut.
Not at all.
They are using their Polaris prototype, which operates daily at over 100 million degrees using a deuterium-helium-3 fuel mix. They are building their Orion plant in Washington right now to deliver power to Microsoft by 2028. But the mechanics of what is happening inside that machine, it is so violent.
It is a dynamic, violent collision by design. In a field reverse configuration, you don't have a single continuous ring of plasma. Instead, you form two distinct FRC plasmoids at opposite ends of a linear machine.
Okay, plasmoids.
Yeah, these plasmoids are high-pressure, self-contained rings of plasma. Think of them as smoke rings made of fire, and they carry their own internal magnetic fields.
So they are self-contained little packets of star stuff.
Exactly. Once formed at the ends of the reactor, massive magnetic coils accelerate them toward the center of the machine at over 1,000,000 miles an hour.
1,000,000 miles an hour, just casually.
When these two high-pressure plasmoids collide and merge in the central chamber, they are subjected to a massive, sudden external magnetic compression. The background magnetic field spikes, squeezing the merged plasmoid.
Like a vice grip.
The pressure and temperature spike instantaneously in that central pinch, crossing the threshold for thermonuclear fusion. It burns for a fraction of a second, and then the process repeats. Pulse, collide, compress, burn.
Hold on, I'm losing the thread here. I understand that smashing them together at 1,000,000 miles an hour creates immense heat. I understand the fusion threshold, but how does that equal electricity?
That's the best part.
Because for the last 300 years, from the Industrial Revolution, from coal to natural gas to nuclear fission, human power generation has essentially been one thing: finding a fancy way to boil water to spin a steam turbine.
It's true.
It feels so primitive. Are we really going to build a miniature pulsating star, fire it down a vacuum tube just to boil a pot of water?
No, and that is the profound, almost haunting elegance of the FRC approach.
Yeah.
We bypass the turbine entirely. We bypass the water. We are utilizing direct electromagnetic energy conversion.
Direct conversion.
To understand why this is so revolutionary, we have to talk about the physical limits of boiling water.
The Carnot limit.
Yes. In the 1820s, a French physicist named Sadi Carnot established the fundamental thermodynamic law that dictates how much energy you can extract from a thermal power cycle.
Right, whenever you use heat to create steam to push a physical object like a turbine blade, you are bound by the Carnot limit.
You lose a massive amount of energy as waste heat. Even the most advanced, hyper-optimized combined cycle thermal plants today only capture about 30 to 45% of the energy.
The rest is just gone.
The rest is simply lost to the atmosphere. We've spent 2 centuries trapped by this thermodynamic ceiling, but Yelian's FRC approach simply steps outside of those laws.
Because there is no heat transfer. But how does the power physically leave the machine?
It relies on the deepest fundamentals of electromagnetism. It works like this. As the merged plasma torus is compressed and reaches fusion temperatures, the actual fusion reactions release high-energy charged particles.
Okay.
This sudden influx of internal energy from the fusion burn causes the plasma to dramatically increase in internal pressure. It wants to expand. It rapidly pushes outward, radiating from the center of the chamber.
So it's trying to push its way out of the invisible magnetic cage that just crushed it?
Exactly. And as this highly conductive, rapidly expanding plasma pushes outward, it physically presses back against the confining magnetic fields generated by the external coils of the reactor. It compresses the magnetic flux outward.
Oh, I see.
Now, according to Faraday's law of induction, when you change the magnetic flux passing through a coil of wire, you induce an electrical current in that coil.
Wait, let me make sure I'm visualizing this right. The plasma expands, which pushes the invisible magnetic field, and the magnetic field physically moving across the metal coils generates the electricity.
Yes. The expanding plasma acts as a piston, pushing against the magnetic field, which instantly induces a massive reverse electrical current in the surrounding coils.
That is wild.
That newly generated current flows directly out of the reactor and back into the very capacitor banks that fired the machine in the first place.
I really want you sitting there right now to pause and think about the unnerving efficiency of this. There is no middleman, no heat exchangers, no giant concrete cooling towers, no steam, no spinning steel blades, just the raw, violent expansion of a star directly pushing against a magnetic field to create pure electricity.
The efficiency is staggering. Because it is a direct electromagnetic process, it recovers 95% of the input energy.
95%.
The implication of that recovery rate is what truly breaks the paradigm. Because they recover almost all the energy used to fire the plasmoids, the machine can generate net electrical power even if the actual scientific fusion energy gain, the Q value, remains incredibly low.
So it doesn't even need to be a perfect fusion burn.
Right. The plasma expands, the magnetic field pushes back, the capacitors recharge. It is a closed, highly efficient electromagnetic loop.
It's no wonder a software giant like Microsoft signed a power purchase agreement for this. It's power generation treated almost like software code, clean, cyclic, bypassing the messy, physical, rusted realities of steam and turbines.
It is a beautiful mechanism, but we must be clear, all of this, the massive tokamaks like Spark, the AI-designed stellarators, the pulsating FRCs, none of it matters without the unsung hero that is actually making this era possible.
The tape?
All of these machines require incredibly strong magnetic fields to contain or compress the plasma. For decades, generating those fields required magnets the size of office buildings, cooled by liquid helium. None of this modern era works without the magic tape.
You are referring to REBCO, Rare-Earth Barium Copper Oxide tapes. This is the material science breakthrough that has taken fusion from massive, stadium-sized government facilities that take 30 years to build, down to compact, commercially viable machines that can fit inside a warehouse.
REBCO is a second-generation high-temperature superconductor. It is the physical foundation of the new fusion economy.
Wait, the formula for this stuff, it's usually a yttrium variant, right? YB2307X, barium and copper. So we aren't talking about rare, exotic space metals mined from asteroids here. We're talking about ceramics.
That is the fascinating contradiction of REBCO. It is a cuprate ceramic. In its normal state at room temperature, it's a relatively poor conductor of electricity.
Like a coffee mug.
Exactly.
Yeah.
But when you cool it down, the internal crystal structure, specifically the copper-oxygen planes, align in such a way that they become flawless, zero-resistance highways for electrons. When we say high-temperature superconductor, we have to be clear about what that means in the realm of cryogenics. We are talking about operating the magnets at 10 to 20 Kelvin.
Which is deeply, terrifyingly cold. That is just slightly above absolute zero.
True. But compared to older first-generation superconductors like niobium-tin, which had to be kept at 4 Kelvin using highly volatile and expensive liquid helium, 20 Kelvin is practically a heat wave.
Because you can just use liquid nitrogen or standard coolers.
You can cool REBCO using standard commercially available cryocoolers. But the operating temperature isn't even the most critical factor here. It's the magnetic field tolerance.
Right, because generating a magnetic cage means the wire generating it is also sitting inside that extreme magnetic field.
Exactly. Older low-temperature superconductors lose their superconducting ability, a phenomenon known as a quench if the surrounding magnetic field gets too strong. Niobium-tin typically quenches and reverts to a normal metal around 30 Tesla.
And REBCO,
however, can maintain its superconducting state in critical magnetic fields exceeding 100 Tesla. It is virtually immune to being overwhelmed by the very magnetic field it is helping to create.
And that leads to what might be the most important mathematical equation in this entire field, the scaling law of fusion power.
Oh, yes.
The power output of a fusion plasma scales to the 4th power of the magnetic field strength. I want to make sure the weight of that equation lands. If you just double the strength of the magnetic field holding the plasma, you don't double the power output, you get 16 times the power output.
It is a cubic expansion of efficiency. This scaling law is the single reason why a company like China's Energy Singularity could build their new HH-70 tokamak and shrink the entire reactor volume down to just 2% of older designs.
2%?
REBCO allows us to build astronomically stronger magnets. Stronger magnets mean we can squeeze the plasma harder, achieving higher density and pressure. Higher pressure means a massive spike in fusion power from a much smaller volume of plasma. The machines suddenly fit inside a standard building instead of requiring a massive subterranean complex like ITER.
It sounds perfect. We have a ceramic tape that carries limitless current and generates massive fields in a tiny space. But, you know, nothing in physics is free. What happens when something goes wrong with the tape?
This brings us to the terrifying mechanical vulnerability of these systems. Operating a REBCO magnet involves pushing immense amounts of electrical current, thousands of amperes, through a tape that is only a few micrometers thick.
Thinner than a hair.
Because it is in a superconducting state and has zero electrical resistance, the tape does not heat up. It can carry that massive river of current silently. But what happens if a microscopic defect in the ceramic crystal, or a slight local temperature fluctuation, causes a tiny section of that tape, even just a millimeter long, to lose its superconductivity?
It enters a resistive state, it becomes a normal metal, and suddenly, this massive river of electrical current, flowing with unimaginable force, hits a wall of electrical resistance. The heat must generate instantly.
Traditionally, in older superconducting coils, the wires are wrapped in electrical insulation to prevent the current from short-circuiting between the layers. Because of that insulation, the current has absolutely nowhere else to go.
It's trapped.
It is forced to push through that new, highly resistive hotspot. The temperature skyrockets from 20 Kelvin to thousands of degrees in milliseconds.
Oh.
This causes a catastrophic thermal runaway. The heat spreads, causing more of the wire to quench, which creates more resistance, which creates more heat. It completely burns out and melts the entire multi-million-dollar magnet assembly from the inside out in a brilliant, devastating flash. It is an instantaneous, total failure of the machine.
Which is why the no insulation, or NI breakthrough, is so fascinating. When I first read about this, it felt entirely counterintuitive to everything we understand about electricity. Normally, you wrap wires in rubber or capped in insulation so they don't short-circuit across each other. But with these new REBCO magnets, engineers realized the insulation was the trap.
Exactly.
So they just took the insulation off entirely. They wind the bare ceramic tapes directly against each other in the coil.
It relies on a beautifully elegant physical dynamic. During normal, steady-state operation, the current flows smoothly along the long spiral path of the REBCO tape because that superconducting path has absolutely zero resistance.
Even though they are touching.
Even though the bare tapes are physically touching layer upon layer, there's a tiny bit of radial resistance between the layers. Turn-to-turn contact resistance. Electricity always takes the path of least resistance, so it ignores the adjacent layers and stays entirely on the spiral zero resistance path.
I try to visualize this like a massive river and a dam. Imagine a raging river flowing through a perfectly smooth, frictionless canyon. That canyon is the superconductor. A quench, that microscopic defect, is like an instant concrete dam suddenly appearing in the middle of the river.
That's a great way to look at it.
In an insulated wire, the canyon walls are solid rock. The water has nowhere to go, so the pressure builds instantly until the dam explodes in a catastrophic release of thermal energy. But in a no-insulation coil, by removing the insulation, we make the canyon walls porous.
Right.
The moment the dam occurs and the pressure spikes, the water, the electrical current, simply seeps radially through the porous walls into the adjacent parallel channels. It bypasses the dam entirely without a spike in pressure and then seamlessly rejoins the main river downstream once it's past the blockage.
That is an excellent way to conceptualize it. The moment the quench happens and the local resistance spikes, the current instantly shifts radially, turn to turn, bypassing the hotspot entirely. The magnet actively, organically protects itself from thermal destruction without requiring complex external sensor interventions.
The machine heals itself in real time. It's brilliant.
It averts the thermal explosion perfectly. However, solving the thermal problem immediately exposed a severe, deeply physical mechanical problem. We are pushing these REBCO magnets to fields of 20 Tesla and beyond. At those extremes, we encounter Lorentz forces.
Lorentz forces. Let's break that down. We aren't talking about heat or electricity anymore. We are talking about raw physical pressure, right?
Yes. A magnetic field does not just act on the plasma. It physically pushes against the very wires that are generating it. Imagine holding two immensely powerful magnets with the same poles facing each other and try to fuse them together.
You can feel the invisible pressure trying to push your hands apart.
Now, scale that outward pressure up to millions of pounds of force. At 20 Tesla, the physical outward pressure generated by the magnetic field is catastrophic. The magnet literally wants to explode outward, ripping itself apart.
The machine is so powerful, it threatens to tear itself to pieces under its own magnetic stress.
Precisely. Standard commercial REBCO tapes, which are usually layered on a thin substrate of hastelloy with a yield strength of about 700 megapascals, simply stretch and tear under that massive strain. This is the mechanical cliff facing the industry.
So how do we stop the cage from blowing itself apart?
To prevent structural failure, developers are having to completely rethink the architecture of the cables. They're moving to advanced, ultra-high-strength alloy substrates. And more importantly, instead of just winding flat tapes into circular pancakes, they're developing CORC architectures, conductor on round core.
Meaning they aren't using flat ribbons anymore.
Correct. They take multiple REBCO flat tapes and wind them helically around a central, small copper core, almost like the strands of a thick rope.
Okay, that makes sense.
This creates a flexible, incredibly strong, high current density circular cable. This rope-like architecture can withstand the massive Lorentz forces, and crucially, it is flexible enough to be twisted into the bizarre, non-planar geometries required for the AI-designed stellarators without snapping the brittle ceramic layers.
Okay, let's take a breath and look at where we are. We've built the cage. We have the silicon brains designing the twisted shapes, the REBCO ceramic tape shrinking the volume, the no insulation porous wall technique stopping the thermal explosions, and the CORC helical cables holding it all together against tearing. We have a functional, compact magnetic cage.
We do.
But now we have to face the darkest, most problematic reality of this entire endeavor. The cage is empty. We have to fuel it.
And this is where the physics of containment meets the brutal reality of nuclear chemistry. The vast majority of the systems we've discussed, from the tokamaks to the FRCs, rely on the DT fuel cycle, deuterium and tritium.
Deuterium is the easy part. It's a stable isotope of hydrogen found in seawater. We literally have oceans of it. We could pull deuterium out of the Pacific for 1 billion years and barely notice a drop. But tritium, there is existential scarcity to tritium.
It is the great bottleneck of the fusion era. Tritium is a highly radioactive, unstable isotope of hydrogen with 2 neutrons. It has a half-life of just over 12 years, which means it decays relatively quickly.
So it doesn't stick around.
Because of this rapid decay, it does not exist in meaningful quantities anywhere in nature. It must be artificially manufactured, typically as a byproduct in heavy water fission reactors.
And the numbers on this are staggering. The entire global civilian inventory of tritium on Earth right now is approximately 20 kilograms.
That's nothing.
That is it. A few handfuls of this radioactive isotope kept in highly secure facilities to supposedly power a global energy revolution. It's completely paradoxical.
Consequently, any commercial reactor operating on DT fuel cannot just operate like a coal plant, buying fuel from an external supplier. There is no supply chain. To survive, the machine must artificially breed its own tritium inside the reactor core while it operates.
Yeah.
It must synthesize its own fuel in real time.
And the way it does this is violently destructive. It goes back to the actual fusion reaction. When a deuterium atom and a tritium atom fuse inside that 100 million degree plasma, they create an alpha particle, which is just a helium nucleus, and a neutron.
Right.
But this isn't just a regular slow-moving neutron. It is a 14.1 MeV high-energy neutron.
To understand the violence of a 14.1 MeV neutron, you have to compare it to standard nuclear fission. The neutrons released when uranium splits in a traditional nuclear power plant carry about 2 MeV of energy. They are manageable.
So 14.1 is just off the chart.
A 14.1 MeV neutron carries 7 times that kinetic energy. And crucially, because neutrons have absolutely no electrical charge, the massive, perfectly sculpted magnetic cage, the REBCO tape, cannot contain them.
They just pass right through.
Magnetic fields only interact with charged particles. The neutrons fly straight out of the plasma, straight through the vacuum chamber, completely ignoring the 20 Tesla magnetic fields, and slam directly into the physical walls of the reactor and the supermagnets themselves.
And when they hit the magnets, they don't just cause physical impact damage. It's not just wear and tear. They cause nuclear transmutation.
That is the insidious, deeply problematic reality of the DT cycle. The 14.1 MeV neutrons are moving with such extreme kinetic energy that when they collide with the atomic nuclei of the HTS magnet assembly, they trigger nuclear reactions within the metal itself.
Wow.
They knock protons and alpha particles loose from the crystal lattice. These secondary ions recoil deeply into the superconducting layers of the REBCO tape. Once embedded inside the solid metal, they capture stray electrons and literally become microscopic pockets of hydrogen and helium gas, trapped completely inside the solid crystalline structure.
I want to really emphasize the absolute horror of this concept from an engineering perspective. The machine is performing modern alchemy on itself. The radiation isn't just heating the machine up, it is actively, elementally changing the composition of the supermagnets into gas.
It's devastating.
Over a projected 30-year operational life, this internal gas accumulation causes the solid magnet layers to swell, deform, and physically delaminate. The mechanical degradation literally halves the capacity of the magnet. The machine is slowly digesting itself from the inside out.
It is an agonizing material science problem. You cannot stop the neutrons from being born, and you cannot trap them with magnets. How do you stop a machine from eating itself?
That's the $1 question.
The only solution is to intercept them before they reach the magnets, and ideally use their violent kinetic energy to solve the tritium fuel scarcity problems simultaneously. This requires the integration of a tritium breeding blanket, or TBB.
This is where first light fusion comes in with their flare architecture. And it is an incredibly elegant, if somewhat terrifying, solution. They use a liquid armor approach.
Yes, specifically, a thick, flowing bath of liquid lithium. In the flare design, the central target chamber where the fusion occurs is not surrounded immediately by solid steel or REBCO magnets. Instead, it is completely enveloped by a rapidly flowing layer of liquid lithium metal.
Like a waterfall of liquid metal inside the reactor.
Precisely. This liquid metal acts as an ablative, self-healing shield. When the 14.1 MeV neutrons fly out of the fusion reaction, they crash into the liquid lithium before they ever reach the structural magnets or the outer walls. The immense physical damage, the kinetic shock, is absorbed by a liquid.
And a liquid can't break.
A liquid cannot crack, it cannot delaminate. It simply absorbs the energy, flows, and reforms perfectly.
But the armor isn't just a shield, it's a factory.
That is the core brilliance of the design. When a high-energy neutron strikes a lithium atom within that flowing liquid, it triggers a specific nuclear reaction. The lithium atom splits, producing helium and, crucially, a new atom of tritium.
And this isn't just about breaking even, right? First Light validated that their neutronic analysis achieves a tritium breeding ratio, a TBR of 1.8.
Which is fantastic.
Meaning, for every 1 atom of tritium they burn in the fusion reaction, the liquid lithium armor catches the resulting neutron and breeds 1.8 new atoms of tritium.
It operates at a massive surplus. At a baseline electrical output of 333 megawatts, this breeding blanket creates a net surplus of 25 kilograms of tritium every single year.
Wait, 25 kilograms?
Remember, the current global supply is only 20 kilograms. A single machine of this design would more than double the world's supply in 12 months. The liquid lithium is continuously pumped out of the chamber. The newly bred tritium gas is extracted and fed directly back into the injector to fuel the plasma. The machine doesn't just sustain itself, it creates the fuel needed to turn on the next machine.
It is the ultimate closed-loop nuclear cycle. The sheer violence of the 14.1 MeV neutrons, the very thing that threatens to destroy the machine, is weaponized to guarantee the survival of the industry. But as I sit back and look at all these breakthroughs collectively, the ultra-high field REBCO magnets, the porous no-insulation coils, the pulsed power switching of the FRCs, the direct energy conversion bypassing the turbine, the closed fuel loops breeding rare isotopes, a much larger, far more intimidating picture begins to emerge.
It really does.
Everything we have discussed about commercializing fusion for the terrestrial grid in 2026 is, in reality, merely the foundational engineering for something much more profound.
You're recognizing the convergence. When you look closely at the specific performance metrics of these technologies, they're vastly over-engineered for simply boiling water or running a steam turbine on Earth.
This is the realization that hit me like a physical weight when looking at this timeline. We think we are just building advanced power plants to keep the lights on, to power data centers, and to stop burning fossil fuels. But all of this hardware, every single piece of it, is the exact technological stepping stone required for antimatter propulsion. We are practicing for the void.
The parallel is undeniable, and the physics communities are deeply aware of it. The exact same ultra-high field REBCO magnets that were designed to shrink tokamaks down to warehouse size are right now being adapted by institutions like CERN for deep space applications. In March 2026, CERN's BaseStep project successfully utilized these portable REBCO-based cryogenic traps for the first macroscopic transport of antiprotons.
Let that sink in. We are taking the most volatile, destructive substance in the universe, antimatter, where a single gram could level a city, putting it into a portable magnetic thermos built from fusion technology, putting it on a truck and moving it.
Furthermore, the electromagnetic control systems, the precise voltage division, and the pulsed plasma dynamics pioneered by Helian energy, the very systems expanding plasma to push against magnetic fields for electricity, those are the exact mechanisms required to build the magnetic nozzles and RF cavities that will channel relativistic exhaust in an antimatter engine.
And when we talk about an antimatter engine, we are not talking about something simple. We have to talk about the ACMF engine. Antimatter-Catalyzed Microfission-Fusion. Look at the ICAN-II concept. This is where human engineering crosses the line into absolute terrifying hubris.
It's incredibly complex.
We aren't just mixing matter and antimatter together in a chamber and riding the explosion like in a sci-fi movie. The mechanics of this engine are an intricate Russian nesting ball of total nuclear annihilation.
To understand why it must be so complex, we have to understand the limitations of pure antimatter. Pure matter antimatter annihilation produces incredibly high-energy gamma rays and neutral pions, which are extremely difficult to direct with magnetic fields for thrust.
Because they just scatter everywhere.
Much of the energy is lost as unharnessable radiation. The ACMF engine solves this by using antimatter not as the primary fuel, but merely as a microscopic spark plug. The geometry of the ACMF fuel target is staggering. You begin with a sub-millimeter pellet.
A pellet smaller than a grain of sand.
Yes. At the very center of this microscopic pellet is a core of deuterium-tritium fusion fuel. That core is wrapped tightly in a thin, solid, subcritical shell of uranium-238. The molar ratio is approximately 9:1.
So you have a microscopic speck of fusion fuel completely encased in a microscopic shell of heavy uranium.
Precisely. The ignition sequence for this pellet is a 3-step process of rapidly escalating violence, requiring timing precise to the nanosecond. First, the pellet is injected into the engine chamber. External particle beams hit the pellet symmetrically from all sides. This violently compresses the uranium shell inward, drastically increasing its density, but it remains stable. It does not react.
Okay, so it's just super dense.
Second, while it is compressed, a 2-nanosecond burst of antiprotons, just a microgram scale injection of pure antimatter, is fired directly into the heart of the compressed pellet.
And what happens when an antiproton physically impacts a uranium nucleus?
Total immediate annihilation. The antiproton and a proton within the uranium-238 nucleus annihilate each other on contact, converting 100% of their mass into pure energy and releasing high-energy pions. This sudden, violent injection of massive energy inside the dense uranium shell instantaneously triggers a localized microfission event. The uranium atoms split, releasing heavy fission fragments and a swarm of high-energy neutrons.
Let me stop you there. We are using a microscopic injection of antimatter to trigger a nuclear fission bomb.
Yes, and that is only step 2. Step 3. The immense heat and pressure generated by the splitting uranium atoms, reaching several kilo-electron volts of temperature, crushes inward on the central deuterium-tritium core. The physical conditions inside that microscopic core instantly cross the extreme threshold for thermonuclear fusion. The DT core ignites, releasing an even larger burst of energy and plasma.
I need to wrap my head around the sheer madness of that sequence. We are using the rarest, most volatile substance in the universe, antimatter, to artificially trigger a nuclear fission bomb, which provides the heat and pressure to instantly trigger a thermonuclear fusion bomb, all occurring inside a pellet smaller than a grain of sand in a fraction of a second. Just so we can magnetically channel the resulting shockwave out the back of a nozzle to push a spaceship. The hubris of that sequence is staggering.
It is the ultimate application of relativistic quantum mechanics to practical aerospace engineering. By using antimatter simply as a catalyst to trigger a microfission-fusion chain reaction, we leverage the dense, harnessable energy of nuclear forces while maintaining manageable radiation shielding and thrust parameters.
It's just so beyond what we're used to.
This specific sequence provides the extreme specific impulses and exhaust velocities necessary for rapid, interplanetary, and eventually interstellar transit. It is the only physical mechanism we currently understand that could push a massive payload to a fraction of the speed of light.
It forces you to stop and consider the sheer heavy weight of this capability. We are living through the transition right now. We are evolving from a species that powered its entire civilization by digging up dead plants and setting them on fire, to a species that engineers non-planar magnetic cages with artificial intelligence, directly harvests electricity from expanding rings of plasma, and harnesses the total momentary annihilation of antimatter to colonize the void.
It leaves us with a profound philosophical burden. We have spent millennia looking up at the stars, wondering how they burn, feeling incredibly small beneath them. Now we have mastered those forces. We've pulled the fire down. We hold the rawest, most fundamental codes of the universe in our hands.
Yeah.
And the immediate, undeniable byproduct of that mastery is the ability to traverse the cosmos. The universe is terrifyingly vast, incredibly silent, and largely hostile to organic life. For the entirety of our history, we were bound by the chemical energy limits of our home world. That is no longer true.
You are the third person in this room right now, sitting with us, listening to this. We built this exploration specifically for you to trace this incredible, daunting path. And so, the question I want to leave you with, the thing I want you to tell me about in the comments down below this track, which of these terrifying, beautiful realities do you want us to explore further? Do you want to understand the silicon mines sculpting those invisible magnetic cages? Do you want to unpack the pure physics of pulling electricity directly from the expansion of a violently colliding plasma? Or do you want to break down the intricate, destructive mechanics of an antimatter engine pushing us out into the dark? Let me know.
If we have truly gained the power to artificially create and contain the core of a star here on Earth, what does that make us? And looking out into the absolute silence and the unimaginable scale of the universe that awaits us, are we truly ready for what is out there?